Okay. I have electromotive force. I have the resistance, Ohm's law. I have the capacitance, C is equal to Q divided by delta V. And now we're going to move on to inductance. So, inductance are the equivalent of the capacitors. Okay, the inductors are the equivalent of capacitors, but instead of storing the energy in the form of electric field, we're gonna store it in the form of a magnetic field. Okay, I'm gonna skip this. So basically, if we go back to this example here, where when the switch is closing, then my current I is increasing, the magnetic field in this loop is increasing. And according to Faraday's law and Lenz's law, then I'm going to have a battery, which is shown here in dashed line, which will come to a positive change. Okay? So basically now, there is a link between the electromotive force E and the time variation of the current I. Okay? Instead of just leaving it like, let's say, like this, what we're going to do, we're going to introduce inductor. Okay, the inductor is simply usually is designed is drawn as a solenoid. Okay, with an inductance defined by L. L is equal to N, which is number of turns. Phi B is the magnetic flux across one area, across the area, and I, which is the current I. So L equal N phi B divided by I is equivalent to C is equal to Q divided by delta V. Yeah, if I assume that N is equal to unity for simplicity, then what I can write is phi B, which is the magnetic flux, is equal to L multiplied by I. Yeah, the amount of magnetic field I'm generate for a given current I, okay, is equal to this current I multiplied by this inductance L, okay, of the inductor, okay. So in the same way where we said the amount of charges I am able to put is equal to the battery I'm using multiplied by the capacitance. Here, the amount of magnetic field I'm able to generate is equal to the current multiplied by the inductance. The same thing, the same concept, but now we're going towards the current instead of the potential difference, and the magnetic field instead of the electric field, and of course the inductance instead of the capacitance. The unit of the inductance is in Henry, okay, and that's our friend Mr. Henry. Okay, now, and this is a bit tricky. In what sense? If I say that my phi B is equal to L multiplied by I, right? This is my phi B, N is equal to 1. L is equal to phi B divided by I, so my phi B is equal to L multiplied by I. According to Faraday's law, E is equal to minus d phi B over dt. I'm sure that you all remember that, okay? Consequently, d phi B over dt, but here, since it's L multiplied by I, so L di over dt plus I dl over dt. Since L is constant, then my d phi B over dt is going to be equal to L di over dt, okay? And so now, this is also very important. This is E equal minus L di over dt, or is another definition of L equal to the electromotive force E di over dt. Why this is very important? Because when I put an inductor into my circuit, okay, and I have a constant current I, okay, constant current I does not depend on time. When I does not depend on time, di over dt is exactly equal to 0, okay? Consequently, no matter what L is, capital L is, my back electromotive force is exactly equal to 0. So, yes, for if I have a, let's say a solenoid, we'll see it a little bit later, okay? Or any other component, which have an L, which has an inductance. This inductance is defined as the total magnetic flux divided by my current I, okay? But, and this is where it's tricky, but this inductor, when I put it in the circuit, it will only exist for the circuit when I is time varying. Because if I is not time varying, di over dt equal to 0, and the epsilon, which is shown here, anyway. But this epsilon, okay, will be equal to 0. So I can put an inductor in my circuit. That would be great. It's okay. I can have an inductor there. I can determine its value. Okay. But it's going to play a role, it's going to exist in a circuit only when I have time. So for example, if I go back to the circuit here, only when the switch is closing or only when the switch is opening, then I'm going to have E is equal to minus L di over dt. Okay? Only when this inductor will play a role. If my I is constant, as if I have a short, basically as if I have zero potential difference between the 2 points. There's nothing there, as if there's nothing there. It's just a wire. Okay, so this is a trick point that you guys need to remember. So this is the sign of a inductor. And here, as I said, L will act only when there is time varying current. Does not mean that L is defined only when I have time varying current. I can define L, I can find it, it's a constant, as we will see. Like for the capacitance, we saw that, for example, for 2 parallel plates, I have C equal epsilon 0A divided by D. It's defined, but does not mean it's going to play a role. L will be defined, okay, but it does not mean that L will be playing a role. Yes, it's do you repeat? Okay, yes, I will repeat that, of course. Yes. Give me a tiny second, let me see what. Let me continue just for a tiny second, and now, of course, I will come back to that. Okay. Cut off. Yes, I know. But I just need a couple of more minutes. Okay. 5 to 10 minutes after the cutoff. Okay. Let's go back. Now, I have a component. I have something. Let's say a solenoid. Okay. We'll see it in a few seconds. We will determine L for the solenoid. Great. L exists. It's there. It's a value. I know it. It's, let's say, 200 or 500 or whatever. Okay. But this L will play a role, okay, as a battery. Yani for the circuit, okay, it will be really just a battery. E is equal to minus L di over dt. Okay. The minus sign, like Lenz's law, it will oppose the change. So if I is increasing, E will be opposite to the electromotive force. If I is decreasing, E will be in the same direction as the electromotive force. Okay? So there's one thing, the definition of the inductance, which can be defined, is going to be a quantity, whatever that thing is. The second thing, which is not as the first, is when it's going to play a role. In a circuit, it will play a role in the circuit only when I have time variation, okay? And this epsilon here, this is not epsilon